Okay, this is problem 31, chapter 23. And it's very similar to the problem that we had gave the recording for, where it was the potential due to a charged disk. And what they're asking for is the potential due to a disk with a hole in it. So if we look at what this problem 23-9 had, it was a disk that went all the way to an inside radius of 0. So if you look at the way they ended up calculating the voltage, let me just basically ended up with something that looked like this. Actually, I'm going to write this down. I think I might have only just had. So this is on page 599. So they integrated from 0 to R of R dr over x squared plus r squared to the 1/2 power square root. So it's similar. We have an inside radius and an outside radius. So the inside, the lower limit is not 0 anymore, and you actually have to treat it as such. So this is like one step backwards. Instead of taking Q and getting a charge per unit area by just saying what charge per unit area is, they took the total charge for the whole disk, and then they divided that by the total area, which would be equal to pi r squared. And so in our case, what we're doing is we are going to let dq, instead of being q divided by the area, we're going to actually specify a dq. That's the infinitesimal charge on the area, which is a ring. In this case, we did an infinitesimal ring. So it went all the way around, but it had just a dr width. So we're going to say the dq, the differential charge, is equal to the charge per unit area times the differential area. So since this is differential and multiplied by a constant, that gives us a differential, just factored. And the charge per unit area, well, actually it should be sigma. It's like more like a rho. So that should be sigma. The area, the infinitesimal area for this, is the circumference, 2 pi r, times the thickness of the ring. Sigma is the charge per unit area. dA is the differential area, which is 2 pi r dr. And so we can substitute both of those. We can substitute for dq, we can put sigma times dA, and then for dA we put 2 pi r dr. Since we are taking a circle of circumference 2 pi r and a width of dr to calculate the area of the infinitesimal ring, so the infinitesimal charge is the charge per unit area times the infinitesimal area, which is dA, but it can be rewritten as 2 pi r dr. Okay, so we can replace dq with that. So we get that integral. So we integrate from the inside radius, which is the radius of the hole, to outside radius, which is the radius of the disk. dq is sigma 2 pi r dr. We have this, which is the distance from the charged ring to the x distance away from the ring, from the disk or ring, depending on which case we're talking about. So sigma is a constant based on the amount of charge that's on the disk. And you can see we've got 2 here and 4 there, so we can simplify that down to a half. The pi's cancel out. Sigma is a constant, so we can take that out of the integral. So we end up with this. So pi's cancel out, and 4 becomes 2. And the integral is r dr over the square root of x squared plus r squared. R is the variable. X is a constant, but it's a constant we're going to change depending on the geometry of the situation. So now we just need to integrate it. Well, we have to use U substitution because this is going to be all U, and this is going to be du, except it's going to be a extra factor. So when we take the derivative of this, this is a constant. X is going to be a constant distance from the disk. So the derivative of that is 0, and the derivative of r squared is 2r times dr. We have r dr, so we want to solve for r dr. Just divide both sides by 2. So for r dr, we can put in du over 2, and for this x squared plus r squared, we can put in u. We also need to redefine the limits in terms of u. So when the radius is the inside radius, which is the, or outside radius, which is the upper limit, u is going to be equal to x squared plus capital R sub 0 squared. Likewise, when the lower limit is, when we integrate from the lower limit in terms of r was r sub I, but in terms of u is going to be x squared plus r sub I squared. So our new integral is, we could factor out the, and I don't know why I did that. Let me fix that. So that should be sigma. And this should have sigma as well. Left that out. Okay. So we have sigma, charge per unit area. And then we have du over 2 and the square root of u. And our limits are x squared plus r sub I squared and x squared plus r sub O squared. So this is just, we can rewrite, we can take the 2 outside, so that'll become 4 in the denominator. Okay, I haven't done it yet. I don't know why, I'm not sure why that was there. Seems like I'm repeating stuff. Okay, yeah, it looks like a repeat. I just didn't put the limits, so let's just get rid of that. Okay, so, and I need to fix that as well. Sigma. Okay, sigma, we get a 4 there because I factored out the 2 in the denominator, so 2 times 2 is 4, epsilon 0. This is u to the minus 1/2, so let's go ahead and stick that in there. Extra step here, not extra, but just, actually let me put a 4 in there, so combining these two. 4 epsilon 0, the integral from x squared plus r sub I squared, this is to x squared plus r sub O squared, and we have u to the minus 1/2 du. So I've taken this, which is in the denominator, with the positive exponent. I moved it to the numerator with the negative exponent. Okay, so I add 1 to the exponent, divide by the new exponent. That's how the power rule works. 4 times 1/2 is 2. So I get 2, and again I have the wrong word in there, sigma. So 1/2 times 4 is 2, sigma epsilon 0, plug in the upper limit, so I get the square root of the upper limit minus the square root of the lower limit, and that's the answer right there. So that's the potential at a point x away from the center line of this ring, which has an r sub I radius, an inside radius of r sub I, and an outside radius of r sub O.